Hi, in this video series we will be dealing with Chapter 1, the real number system. So we will be talking about numbers, the sets of numbers, how to deal with numbers, how to manipulate them, the properties that we have, the rules that we have, and then we'll be talking about some properties of groups of numbers. I mean some subsets of numbers, parts of the whole set of numbers. Okay, so these ideas we'll discover them during the course. But to start, I want to say that you know that all mathematical tools and ideas are used to explain our everyday life. So they are a need. Let me explain myself. If you take the number 10, for example, it's a number that represents 10 items. It's a language that you are using every day. So if we want to buy chocolate, 10 bars of chocolate, you will not say to the guy, give me a chocolate and chocolate and chocolate and chocolate and chocolate 10 times. No, you will tell him, give me 10 chocolates. If you don't know the word 10, you would not be able to use it, and you would have to say, give me chocolate and chocolate and chocolate 10 times. Okay, so when you have this math language, you are using it every day to simplify your life and to make things easier, and to be able also to construct new systems and new theories according to the basic ones you already know. Okay, so that's why we have to look at the mathematical concepts from this perspective. They are explaining our everyday life. They are explaining the physical phenomena. Numbers are physical. You go to buy apples, you buy 10 apples. It's a physical thing that you are representing with this number. Okay, so that's why from this perspective, let's look at the use of numbers and why we have different sets of numbers. First, of course, they are introduced first. Numbers were introduced first to represent things we are dealing with. That's why the most natural way to introduce a number is the whole number. I mean a number without the decimal places, like 1, 2, 5, 10, 11. Okay, because first we needed to represent the number of things we are using. Give me 10 apples, take 5 bananas, etc. So the first and most natural set of numbers is exactly the natural set that I call n, which is the numbers 0, 1, 2, 3, etc. without decimal places, positive numbers from 0 to whatever you want. So this is the first set of numbers. These are the natural numbers, or we call them also the whole numbers, because they are whole. There is no decimal places. They are not parts of numbers. Okay, this is the first set of numbers. Now, be careful that in some references, the natural numbers are considered as being the numbers from 1 to infinity, without the 0. And the whole numbers are considered to be the numbers from 0 to infinity. So it's the natural numbers plus the number 0. But it depends on the reference. Here in our course, we'll call them all natural numbers. So for us, natural numbers is the same as whole numbers. Now, of course, one noticed the need of negative numbers, and it's also a natural need. Why? Because let's say if I want to exchange bananas with apples, I would give the guy 3 bananas, he will give me 5 apples, whatever. And if I don't have the bananas today, I will tell him, give me 5 apples and I will give you tomorrow 3 bananas. So if he gives me the 3 apples or the 5 apples, I will be, my statement, let's say, will be minus 3 bananas because I owe him 3 bananas. So it's a natural need to have negative numbers. Okay. Mathematically speaking, if you want to solve the equation, I don't know, n plus m equals 0, So if you want to add two things and to obtain 0, these two things cannot be both positive. They should be one as a positive number and the second one as a negative number. That's why we need to introduce another set of numbers, which are the integers. So I will put a bigger set like this. I will call it Z. It's the set of integers, and it contains all the numbers like from -infinity, -2, -1, 0, 1, 2, etc. So these are the integers. They contain all the natural numbers, and we add to them all the opposite numbers to the natural numbers, which are the -1, -2, etc. But also we still have a problem. We cannot represent until now parts of things. We have only whole numbers, in the sense that we can only deal with a whole thing. I mean, if I want to give someone a pizza, until now I can give him one pizza, two pizzas, or nothing. But I cannot give him half of a pizza, because I don't have a number system that represents parts of numbers. So we need something else. So we define also the set of parts of numbers, let me say. So we define also the rational numbers set. The rational numbers set will be something that includes all the sets that we have defined before. So I will call it Q. Okay, so Q is the rational numbers set, and it contains all the numbers that can be written as the ratio of two integers. So they are all the numbers are that can be written as P over Q, where P is an integer and Q is an integer, or it can be also a natural number. I will explain later why. So it's practically all the numbers such as 1 over 2, 3 over 4, -5 over 6, 7 over 8, 100 over 102, whatever. Okay, so these are the rational numbers, and as a conclusion, they represent what? These numbers represent all the numbers, all the decimal terminating numbers, and decimal terminating numbers are the numbers that have decimal places, but they are terminating. They don't have an infinite number of decimal places. Okay, or the decimal non-terminating numbers but periodic. So I will rewrite it. Decimal periodic non-terminating numbers. Okay, so in the rational number set, of course we have the integers, because any integer can be written as a ratio of two integers, like for example 2 over 1, it's the number 2. Okay, so it contains all the integers, all the decimal numbers with terminating number of decimals, or all the decimal numbers that are non-terminating, but they are periodic, such as, for example, let's take here it's 2.148, and in the periodic non-terminating numbers we have something like 2.787878, etc. Also, it can be like 2.314828282, etc. Okay, so these numbers are rational, so they can be written as a ratio of two integers. We can learn how later. It's not our issue right now, but you know what, you can search for it online. Go and search how to write rational numbers as fractions. I mean, if you have a decimal number like 2.148 terminating, or if it's non-terminating but periodic, look for it online, learn how you can write it as a ratio of two integers. Okay, so these are the rational numbers, and people for some time they thought that that's enough. We can have rational numbers and that's enough, that we can represent any value in our practical, real, everyday's life. Okay, but that was wrong. In fact, if all the numbers were rationals, it means that any number, any decimal number, we can add it q times to obtain an integer. If a number can be written as p over q, okay, then if you multiply this number by q, so if you added q times, you will obtain p. Which means that if you take, for example, a square whose side is equal to 1, and if you take the diagonal of this square, the diagonal of this square will be equal to a number that if you multiply it by itself, it will give 2. So this number will be radical of 2, will be denoted radical of 2. So it's a number that if you multiply it by itself, it will give 2. They thought for a long time that this number, if you multiply it, or if you add it sometimes to itself, it will lead to an integer, which means that it can be written as a rational number, as a ratio of an integer over a natural number. Okay, again, this means that if you multiply radical 2 by q, or if you add radical 2 q times to itself, it will lead to an integer. Okay, but we can prove that this is wrong. Even if you add radical 2 as much as you want to itself, you will never reach an integer, which means that we have another class of numbers that cannot be written as p over q. This proof, we will do it later, okay, to prove that radical 2 is not rational, cannot be written as p over q. And this kind of numbers, we'll call them the irrationals. Okay, and these numbers, so they don't belong to the set q. That's why we go back here and we will add a new set of numbers, the irrational numbers, such as radical 2, radical 3, the number pi. Okay, so these numbers are decimal numbers, non-terminating and non-periodic. So they are non-terminating, non-periodic decimal numbers. So they have a decimal part, they don't end, and they are not periodic. These are the irrational numbers. So if we combine everybody in this graph, so all these numbers together, we will have the real numbers. So real numbers are the rational numbers and the irrational numbers. That's why the set R will be equal to Q together with the R minus Q. The R minus Q is the irrational numbers, and the Q in here is the rational numbers. Okay, and the U in here is the reunion of both sets. It's these elements and these elements put together in one box, which we call the real numbers set. Let me also point out something, is that if we have a rational number R that can be written as P over Q, and another rational number R prime that can be written as a ratio P prime over Q prime, saying that R is equal to R prime does not mean necessarily that P is equal to P prime and Q is equal to Q prime, because you know a fraction, you can multiply it, you can multiply the numerator and the denominator by the same number and the fraction will not change. So it means that PQ prime is equal to QP prime. Okay, so they have the same, it's the same ratio but different numbers. So of course the fraction or the ratio P prime over Q prime is equal to P over Q multiplied by a given number at the numerator and the denominator. Let me also point out that the graph that we drew in here for the sets lead us to the following conclusions. We have the set of natural numbers that is included in the set of integers, which is included in the set of rational numbers, which is included in the set of real numbers. This is the sign of inclusions of sets. So it's a box that is within another box. And let us also point out that if you take the set of rational numbers and the set of irrational numbers, which is written as R minus Q, this minus means the minus between sets, so it's the set of real numbers deprived, which means from which we remove the rational numbers. These two sets does not intersect. There is no rational number that is at the same time as an irrational number. So we can write that Q intersection, this is the sign for intersection, the set R minus Q is equal to phi, which is the empty set. So there is no intersection between the rational numbers and the irrational numbers. So for example, 0 is rational, it's not irrational. Radical 2 is irrational and it's not rational. Okay, so these information I explained, you can find them in this first page. You will read it carefully, and at the beginning of the next page of the chapter that you have.